Objective of this video is to explain the place slenderness limit in terms of plasticity limit lambda EP and yield limit lambda EY, and we are look at some formula to calculate the effective section modulus. Now first we can talk about the flange. Now in the case of flange, when we take, generally we are working on the I-beams. So when we take the flange, that is when we take the I-beam bend on about x-axis, the flange, that is flange, this is web, and this is bottom flange. So this flange generally subjected to uniform compressions. Only one longitudinal edge is supported. What does it means? That if I take the I-beam, in here we have a I-beam which is one longitudinal edge. If you are looking at here, the one longitudinal edge along this one is supported by this web, and this edge is free. So generally we are working with these two, with this outstand. Now we generally have worked with hot roll section, so all the universal beam and universal columns are hot roll. So if I have one steel tables that we're going to use it to extract the informations, they are hot roll section. Those are universal beam and universal columns. And for hollow section, for circular hollow section and square hollow sections, they are cold formed. Now this lambda EP and lambda EY stand for plasticity slenderness limit lambda EP and yield slenderness limit lambda EY. Now this lambda EP and lambda EY for this case, which is the flange. So when we want to find the slenderness limit for the flange, we are using the table 5.2 on page number 51. Now there are 4 rows: row number 1, row number 2, row number 3, and row number 4, and row number 5. So there are 5 rows. So last one is circular hollow section. So we mostly, let's say, talk about the plate one, that is in the I-beam. So that is 4 row. Now I'm explaining first row. When you can use the first row, when you are talking about this flange. When you're talking about flange, the first row you need to use it. Now that flange under the uniform compression, as I mentioned, so when you bend it, this will comes if you bend it, if you bend these I-beams on the about the x-axis, this will comes under the compression. This comes under bending. So if you bend like this in this way, if you bend about x-axis this way, this top one under compression and bottom one under tensions. So that's what they mentioning here, and that is hot roll sections. So lambda EP plasticity limit is 9. That's what we written here, lambda EP 9, and lambda EY is 16. Lambda EY is 16. That is in table 5.2 on page number 51. Now I already explained it, this one in the using the I-beams, that we generally, for the case of flange, we are working on the outstands here, and that has a one edge supported by this web, and this edge is free. So this is a longitudinal edge, and that's one longitudinal edge is supported, and this one is free. That's what this case for the first that is first row. Now move on to the another case when we want to look at the second row. Now I'm talking about the second row. When we gonna use the second row? Now when the beam is bent about y-axis, then in that case only we need to worry about the flange, and this flange has no supports. As you can see, if I bend it about the y-axis, this flange has no supports, right? Unlike the previous case, there was a support, and in that case maximum compressor at unsupported edge. If I take this one, this I-beam, so when we bend about this axis, now we try to bend like this one. So there is no supports for these flanges. So if I bend it like this one about the y-axis, so that is y-axis, and if I bend it, this has no supports. That's what it says that. So maximum compression and unsupported edge, so there is no supports, and it's bending about y-axis only. And it's bending about y-axis only, need to worry about flanges. So we need to just talk about flanges. And in that case, we, as I mentioned, so now we are talking about this second row, where it says the first one is longitudinal edge 1 is supported, but in second case, as you can see, they have same longitudinal edge is supported one, but you can see maximum compression at unsupported edge and zero stress or tension at unsupported edge. That's the difference between uniform compression and this one. So in that case, you are using the hot roll sections. We are taking lambda EP value 25, lambda EY value 25, lambda EP value 9. That's what written here, lambda EY 25 and lambda EP, we can write it lambda EP value 9. Now next one, we are using the third row, that we have this web where we would like to use it. Now the case of web, we are using this fourth row. As you can see in here, we are going to use this fourth row now. Now in the fourth row, we have a longitudinal edge supported where both and this one flat, compression at one edge and tension at another edge. So what I'm trying to say here, that when you bend it about x-axis, this top one undergoes to the compression and this one tension. So when I want to work about wave, we have this case where compression at one edge and the tension at another edge. It has a lambda EP value of 82 and lambda EY value of 115. So that's what written here, and compressor at one edge and tension in other edge, both edge are supported. So what happened here, if I show it in the case of I-beam, we are talking about this web. As you can see, this longitudinal edge of the web at bottom, it's supported by this one, and this top one, which is going across this one, or you can say this edge under to this one, is also supported by this one. And when I bend it, this will goes under compression and this will goes under tension. So one edge is under compression, another edge is under tension, and both edge are supported. So that's what it is. Fourth row is explaining. Both edge is supported, is flat, compression at one edge and tension at another edge, and it has 82 and 114. So that's the case when we use the wave. Now we have some equation to use to find the effective section modulus when you have a compact sections. For example, when is it made of the very thick plates, so in that case it's become compact and is fully effective because it's reached the plastic moments. Now to calculate the effective section modulus, we have an equation, moment of inertia over y maximum. So y maximum is, for example, if you are talking about this from the centroid to the top edge, that is a y maximum, and moment of inertia we can calculate using the mechanics of solids. Now how do we able to find this one? So ZE has a unit of meter to the power 3. Now it should have a minimum of 1.5 ZS, that is given in the Australian standard. For the case of compact sections and ask you to find the section modulus, we have equations. As you can see, effective section modulus shall be lesser of S and 1.5 Z, where S and Z are plastic and elastic section modulus respectively. So where we gonna find these values? So if you are using this, if you are checking this one still tables, and in that one still tables, on page number let's say 14, on the page number 14, for various universal beam sections, if you look at about x-axis and about y-axis, you have a value of zx and you have value of sx, and you have value of zy and sy. That's how you obtain these z and s values. Now for non-compact sections, we have a I think intermediate, like it's not thin or it's not thick plate, so it's a intermediate cross sections, and we need to use the interpolations to do it here. Now ZC values, we can get 1.5 Z to S, minimum of this one, and this equation is taken from section 5.2.4 non-compact sections. On page number 51, we have these big equations where ZC is obtained as is for the compact section, so it should be 1.5 Z ZS. And the last one that we like to talk about is the slender sections. Now case of the slender sections, its effective section modulus is very low, the lowest among the last two, which is compact and non-compact, and slender section is made of very thin plates. and the information is given on the close. This equation is given in the close line 5.2.5 on page number 51, where we are reducing the effective section modulus by this ratio, and that's reduce effective modulus appropriately, and it's buckle before yielding. Thank you.